In the world of science, we're asked to make a lot of promises. Promises about progress and promises about privacy. But what happens when one of those promises, a digital one, locked away in a database, gets broken? Today we're talking about the exact moment the promise of genomic privacy was completely shattered.
So let me ask you this. Can you really hide a name inside your DNA? For years, the entire scientific community basically said, yes, of course. They thought if you just stripped a name off a genetic sequence, you'd created a totally anonymous, untraceable piece of data. They were sure your identity was safe. But, well, were they right?
Look at that number. Over 50. That's how many people had their identities pieced back together from a so-called anonymous public DNA database. This wasn't a guess, it wasn't a theory, it was a real-world demonstration. The mask of anonymity didn't just slip, it was ripped right off. And 2013 was the year it all came crashing down. Researchers at the Whitehead Institute published this bombshell study showing they could take anonymized genomic data, mash it up with other info you can find online, and boom, put a name right back on the sequence. Suddenly, the ghost in the machine had a face. Okay, so let's really get into this because how this happened tells you so much about data itself. We're not talking about a security breach here, like someone hacking into a server. This was about the very idea of what it means to be anonymous. So what in the world is re-identification? Honestly, it's just digital detective work. It's the art of connecting the dots. You take one anonymous data point over here, another public piece of information over there, and you keep connecting them until that anonymous dot suddenly has a name, an age, maybe even a home. No hacking needed, just really clever data analysis. And the method they used was it was brilliant, and it was shockingly simple in its logic. See, it takes advantage of the fact that we all leave these little digital breadcrumbs scattered all over the internet. And it turns out those breadcrumbs can lead right back to our most private data. Here's the playbook. First, they looked at the Y chromosome. That gets passed down from father to son. And you know what else often gets passed down that way? A surname. So they matched that genetic data against public genealogy websites. The ones where people are happily posting their family trees. Just like that, they had a last name. From there, all it took were a few other clues from the dataset, like the person's age and state, and that was usually enough to find the exact individual. And this is absolutely key. The researchers here, they weren't trying to expose anybody. They were trying to expose a massive flaw in the system. It wasn't some kind of malicious attack, it was a mathematical proof. They were showing, with cold, hard data, that the privacy rules everyone was counting on were built on a house of cards. Now, to really get how this was even possible, you have to rewind. We've got to look at the history of how this kind of data was stored and shared in the first place. Because the problem didn't just pop up in 2013. Nope, its roots go way back, right into the architecture of our very first scientific databases. It all started so simply, handwritten lab notebooks. But as technology got better, we moved these powerful relational databases to handle just insane amounts of data. Then, to speed up science, researchers built these huge data sharing portals. But through that whole evolution, one critical, untested assumption was carried along for the ride. The belief that if you just remove a name, you've made the data anonymous. The technology for sharing data was moving at light speed, but the science of protecting it was stuck in the past. And right there, that's the core mistake. With other kinds of data, maybe you can strip out identifiers. But with genomics, the data is the identity. Your genome is fundamentally uniquely you. Removing your name from your genetic code doesn't make it anonymous. It's like sanding the serial number off the Mona Lisa. You're still going to know what it is. So, the 2013 bombshell drops. The flaw is out there for everyone to see. What happened next? Well, the fallout forced everyone to completely rethink data privacy, what consent even means, and what responsibility these big institutions have when they hold our most sensitive information. The impact was immediate and it was widespread. You had individuals who donated their data, promised anonymity, who are now exposed. The National Institutes of Health, the NIH, they scrambled to change their data sharing policies, restricting access. And it kicked off this massive global debate on ethics that, frankly, we're still having today. This event really created a before and after moment. The old way of doing things, just strip the name, get a one-time consent, and assume everything's fine, that was over. The new model is way more robust. We're talking tiered access, so only trusted researchers can see certain data, and consent forms that are brutally honest about the risk of being re-identified. So what did we learn from all this? First and most importantly, genomic data is just identifiable, period. We now know that consent forms have to spell out the risks. And we learned that privacy isn't a yes or no question. It's a probability, a spectrum of risk. But maybe the biggest lesson is that our ethics have to keep up with our databases.
And that leaves us with one last really challenging thought. Your genetic data is permanent. It doesn't change. You can't just request a new genome if yours gets compromised. So in a world where data lives forever, and where new technologies we can't even dream of today might exist tomorrow, can the consent you give right now ever really be considered permanent?